Hi, welcome to the first video of hopefully a series of videos that we'll be releasing this semester to help further explain these complex topics that we introduce in lecture, or just to help students, help guide students' approaches when doing the problem set. So today's video will be about disjoint sets, and otherwise known as union find, and this will be very helpful for homework 2 question 1. So let's jump straight into it. What is a disjoint set? So a disjoint set is a data structure that supports these two main functions. One is unioning two items together. So you have item U, item V, and by calling union on it, you're basically saying that these two belong in the same set or in the same group. The next function it supports is find. So find takes an item and returns the set that it belongs to, represented in some form. And this function can be adapted to check, say, if two items are connected or if two items are in the same set. A way you can do that is you call find on U, then you call find on V, and you just compare the output. If the output is the same, that means they belong to the same set, meaning they are basically connected. So let's run through a quick example to see why this would be even helpful. So say we have here we have Duffield, here we have Upson, and we know we can walk from Duffield to Upson. So let's connect them using union. And then we have Rhodes and we have Upson, and we know we can also walk from Upson to Rhodes, so we connect them. And now we ask the question, is Duffield connected to Upson? And the answer is yes, right? Because first of all, we connected them directly up here, but we also know that we can walk from Duffield to Upson, right? Now the next question, is Duffield connected to Rhodes? And even though we did not connect them directly, transitively, they are kind of connected through Upson, so this is also true. And if we think about it, we can also just walk from Duffield to Rhodes, right? Even though we're just like walking through Upson. So yeah, now let's add some more buildings. So here we have Klarman, here we have Temple of Zeus. Although Zeus is kind of inside Klarman, but let's just forget about that for now. So yeah, we can kind of walk from the building of Klarman to the Temple of Zeus, so they're connected. And now we ask, is Zeus connected to Upson? So, we know that physically they're very far apart, and we also can just see that these two are part of two different sets. So the answer is no. But the purpose of building this disjoint set algorithm, this disjoint set data structure is so that, this data structure also knows this piece of information, and we can just query it by calling these two operations. Cool. So now let's move on to the why. Why are we learning about this? And let's motivate this using this quick example here of a graph, and say we're trying to find the minimum spanning tree. So in class, we learned about this algorithm called Kruskal's. Kruskal's algorithm is a greedy algorithm that helps us find a minimum spanning tree on a graph. So the algorithm we learned in class is an algorithm that runs in m log m time, where m is the number of edges in our graph. So here will be 1, 2, 3, 4, 5, 6, 7, 8, 9. And the algorithm, kind of paraphrased, would basically be like this, right? We basically consider the edges in terms of ascending weight. So we start from 1, then we go to 2, then we go to 3, etc., etc. And we only add these edges to this tree that we're kind of growing as we go if they do not form a cycle. So let's think about the specifics if we were to actually implement this algorithm. So considering the edges in ascending order of weight, a way of doing it is kind of just jumping around the edges, but definitely a smarter way would be to use some form of sort and then just iterate linearly. So the sort we know is m log m, and this iteration is going to be, we're going to have to consider every single edge, right? Because we never know if, say, like the last edge we're going to add is going to be part of the MST. So we need to check all the edges. So that's going to be an O of m iteration going on here. And this is a loop, right? Because we're considering each of the edges. So that means inside this loop, when we're kind of checking if we form a cycle and then adding it to the tree, that needs to be O of log m time. Because if it's any worse than that, let's go back to our previous slide, we see that we can no longer achieve this m log m time, right? Because the outer loop is O of m time, meaning the internal loop must be, can be at most O of log m time. And so if only we have a way of keeping track of the structure of something that we already have, being the tree, and something that we want to add to it, being a new edge, and seeing if this edge, or the node that I'm kind of adding, is already connected to my tree. Because if it is, that means I formed a cycle. And that sounds very similar to something that the disjoint set data structure can help us resolve. So that's the motivation for kind of learning about disjoint sets. But it's also very applicable outside, say, just the Kruskal's algorithm, say in organic chemistry, thinking about connectivity of things. And it's a very, very important and powerful data structure to add to your arsenal. Cool. So now let's go back to the disjoint set data structure. And let's think of a very naive implementation first, right? So I'm keeping track of sets, so why don't I just keep track of it in terms of a list of sets, right? That sounds pretty intuitive. And so down here, I have a visualization of what I have up here, but it basically is saying that 0 and 1, they're a set, 3 and 4, they're a set, and 2 is by itself. So that's represented down here. So let's run through the runtime of kind of what this implementation would have. So to create it, it would take O of n time. And this is okay because we need to make sure that every element is initialized. So that's fine. However, we notice that union / joining items together takes O of n time, right? Because in the worst case, I have n over 2 items in one set, n over 2 items in the other set. And the way I'm kind of joining them is I iterate over one of them, and I just kind of do like set.add or whatever language you're using. But the idea is that you would have to go over every element in one of the sets and add them to the other set. So the worst case of this implementation would be O of n using for union. And finally, what is particularly bad about this implementation is when you're calling the find function, this also takes O of n time. Because in the worst case, where we have all the items fully disjoint, in order to find what set an item belongs to, you have to iterate over every single possible set. So say, for example, you're checking if 0 and 1 are connected, but I have a lot of other nodes. Say I have like 100 of nodes here. What you would have to do is you have to iterate over every single node, iterate over every single set in your list of sets to see whether or not 0 and 1 belong to the same set. So that's also O of n. Now, some optimizations we can do here, right? So, there's a lot of iterating going on. So that's something we can maybe think about fixing. So can we structure this slightly differently, right? Can we store a little less information and have to iterate a little less? And surely we can. So this is the slightly better approach, also known as QuickFind, that is introduced in the textbook from pages 152 to pages 154. So the idea of this implementation is that instead of using like the actual set structure in whatever programming language you're using, we kind of represent them in the form of a components array. So basically, initially we have the values stored within the data structure being the names of each elements, but now we basically are using the indexes of this array to represent information about that item. And so what is stored in this array is very similar to like an ID for the set. So if at index 0 and index 1 they have the same ID, that's basically saying that item 0 and item 1 are connected. And so here we can see 3 and 4 are connected, therefore they have the same set ID. And then 2 is by itself, so it has another different ID. And this ID can be anything you want. It doesn't have to be 0, 1, 2, it could be anything. But the idea is that they have to be unique to the set that they are representing. Cool. So, sorry, I skipped ahead there, but let's consider a quick example of how we are to kind of do the union operation using this data structure. So say I'm connecting 2 to this node called 1. The idea is that after I make this connection, 0, 1, and 2 are going to be in the same set. And so a way I can do that is I change the ID that's stored at 2 to be 0, because now they all share the same ID. But of course, I could have also just changed the ID of 1 and 0 to set them to be the same ID as the set that 2 initially was in. So I'm changing it over here. And either way is fine if we were to implement the disjoint sets using this specific implementation, basically a components array. But we notice that, in terms of like actually changing values using code, we realize that changing the set ID of the set that's smaller is always better, because if we end up changing less things. So that's a small optimization we can make using this approach. So let's quickly analyze the runtime of using this approach. So again, the constructor is going to be linear time because we need to go over every element and create a slot for it in the array. So that makes sense, and that's fine. However, when I'm doing union, we still have this worst case of joining two very, very big sets, right? Because again, if I have a set of size n over 2 and I join it with another set of size n over 2, I'm basically kind of going over n over 2 items in the array, and I'm changing n over 2 items in the array. So that, in terms of big O notation, is still going to be linear time. But the benefit of this approach is now when I'm kind of looking for what set an item belongs to, I no longer have to iterate over all the sets. Now I can just look it up directly. Say, for example, I'm looking for what set 1 belongs into. I just go to index 1 of my components array, and I immediately see that it has a set ID of 0, right? And so say I'm trying to see if 0 and 1 are connected, I just call find 0, which is instant, constant time, and I call find 1, which is constant time, and they both return the ID of 0. So I know that they are connected. So this implementation really speeds up the find operation. However, we notice that the union is still really, really, really slow. And if we actually go all the way back to the kind of Kruskal's algorithm here, we notice that in this part, right, not only are we seeing if adding an item to, adding an edge to this tree that I'm growing will form a cycle, and that probably includes some calls to the find function of the disjoint sets data structure. But we're also trying to add things, so we're basically updating the sets as we're going. So if we were to use a disjoint set data structure here, we would also need to have the union operation be of log m time. Otherwise, if we have a union operation of log m time, a union operation of O of n time, no matter how fast the find operation is, we would still be dominated by the runtime of the slower one. So now we need something to kind of fix this quick find. And here, right? So we noticed one thing that we found really redundant was that when I'm joining two arrays, right? When they're very, very big, I have to change all the values in that array. So is there a way that I can change less values in that array? And so a way we can solve this problem is instead of again like restructuring the way we store the items, we can actually just change the values that we store. And instead of kind of storing an ID for all the elements, we think of them as pointers. So let's consider this example here. It's the same example. 0, 1 is connected, 3 and 4 is connected, 2 is by itself. And instead of just giving them an ID to store, we think of them as pointing to some form of parent. So let me just arbitrarily say that 0 is 1's parent and 3 is 4's parent. We can also flip them around and have 1 be on the top and 4 be on the top. It doesn't really matter for the sake of this example. And so what we actually store in the array here is kind of this parent hierarchy, where 1's parent is 0, that's why we store 0 in index 1, and 4's parent is 3, that's why we store 3 in the 4th index here. And so just to note that I'm not actually kind of saying that these graphs now have to be directed. It's just that when we visualize them, the good way to think about them is that they're directed. And how about for the ones that, what do we store at the points where they no longer have a parent, right? Or say if 2 is by itself, it doesn't exactly have something to be connected to. There we just store some value that we can not be confused with. So here we store a negative value, right? Because we know that an array does not have a negative index. So when we see a negative value, we know that it is the parent. So how does this change the implementation for the find function and the union function? Oh, sorry, I skipped that. So now if we think about the find function, right, like what was the purpose of the find function? The purpose of the find function was to uniquely return a representation of the membership of these items. So if I call find on an item and find on another item, if they're in the same set, I want them to return the same value. And in this example, what we can do is we can just return kind of the grandparent if we have, say, multiple children in this structure. So if I call find on 1, it will return 0 because that's the kind of the main parent. And if I call find on 0, that will also return 0 because it is also the main parent. So this find function now is kind of this trace of lineage going all the way to the top of the parent, and when we reach the parent, we just return the index of that parent as the representation of the set. And well, how does the union structure work, right? So now we know, right, if two items are kind of in the same set, they'll kind of be in the same tree, this directed acyclic graph. then when I'm unioning them, I want to basically join these two trees together. I want to merge them together, right? So let's go through an example to make this clear. So using this representation, if I were to join the node 2 with the kind of set of 0 and 1, what I'm basically trying to do here is I want to join this 2 node with the 0, 1 kind of tree over here to make them in the same group. And so what actually happens in terms of like when we implement it in the code is that 2 no longer stores the value of -1, meaning it has no parent. Now it does have a parent, right? Because it's part of the same set that 0 and 1 is, and the parent that they have is 0. Now there's this important distinction that we want to make. So over here, when I said I'm connecting 1 and 2, why did I assign 0 here instead of 1, right? If I assigned 1 over there, right, that would correspond to kind of 2 pointing to 1, right, and then 1 then pointing to 0. And that would actually also be fine, right? If we were to kind of think about this in terms of set membership, if I were to call find on 2, that would return 0 here. If I call find on 2, that would also return 0 here. So in terms of the functionality, they're actually the same. But the reason why the right-hand side implementation causes an issue is because then the tree, there's no invariance that we can have on the tree to make sure that it doesn't grow linearly. And we can show this with this example here. So say if now I connect item 2 and 3, right? That would basically mean that I kind of take 3 and I stick it onto the bottom of 2. And then I call, say for example, I call find on 4, right? Now I have to trace through the entire tree, and that involves all the nodes, right? This is a very linear looking tree. And this, say for example, I have now n elements, and every single time when I join them linearly. This would lead to a lot of very big issues when I call my find operation, because the worst case scenario would be traversing every single possible element. So how do I fix this? The idea is that every single time when you're merging these trees, right? So basically whenever somebody calls the union operation, I want to make sure that I'm not assigning the value of the 2 items that they're calling union on. So over here, if I call union on 1 and 2, right, I'm not going to assign the parent of 2 to be 1 or 1 to be 2. I will pick one of them, right? I call find on that set, and I take the grandparent of that and I assign that to be the parent of the other set. So in this example here, I would call find on 0, 1, right? That returns 0. And then I assign the parent of 2 to be 0, right? And so the difference, in this small example, it doesn't make too big of a difference because the tree is rather small. But in a much larger example, right, this will kind of prevent the issue of this linearly growing tree. So that's one important tip if you choose to implement kind of the data structure this way for the homework. And another tip is that you want to make sure that you're adding the smaller tree to the bigger tree. Because if you continue with the method that I mentioned just now of calling first calling find on that tree, getting the parent of the tree, and then kind of using that to update the values in the array, right? So in this example, we called find on 0, 1, and we use 0 as the new parent that we're assigning, right? You want to make sure that, say you have 2 trees, or there's 2 sets, right? You call find on the smaller one, because at the end of the day, right, you're just merging them together. So it doesn't matter which one you call on, but, just because the find function, as we will see later as well, scales with respect to its input, you want to call on the one that's smaller to save runtime. Okay, so now the next question is, how do I know which one is smaller? So one common way of doing this is instead of just storing -1 as the parent, you can have the parent store the size of the tree. So over here we see that 0, 1, 2, this is a tree of size 3, and 3, 4 is a tree of size 2. So we kind of have the values in the array reflect the size of the tree, and based on looking at the parent, you kind of see which one is bigger. Another way of doing it is you just have a separate array that keeps track of the size. Both methods are fine. Okay, cool. So that wraps up the kind of improved way of implementing this disjoint set data structure. And if you want to read, so there are some details that I skipped over, but I tried to go in as much depth as I can for the implementation part. So if you want to know more about the proofs of the runtimes that I'm about to discuss, you can feel free to read the pages 154 to 155. But the idea for the constructor is still the same, right? We need to make sure that we have a slot for each of the items. But now the find operation, so I skipped the order here. Instead of going from union to find, I'm going to look at find first. Now the find function here is basically a trace from the leaf all the way, the bottom node all the way to the top node, the grandparent, and I'm just going to return that grandparent as the set ID. Now, the reason why we can guarantee of a log n runtime has to do with the fact that every single time when I'm growing and merging the tree, I ensure that the height never grows more than at a rate of log n. And the actual proof can be found in the book, but I'm just going to gloss over the detail here. And now, since the union operation, as I mentioned here, with kind of the idea of keeping the tree as short as possible, would involve a call to find first before your union. Since I'm calling find before I actually join them, I would have to consider also include the runtime of find. So that's calling find and then updating one value in the array. So that is login time plus constant time, which is ultimately login time. Cool. So this wraps up everything for how you would want to implement the disjoint set data structure. And hopefully you found this useful for the problem set. Now, I'm going to talk a little bit more about this further optimization you can do called path compression, but note that this is not required to kind of pass all the test cases for homework 2 question 1. But if you find this cool or you want to learn how to actually implement this, you can feel free to keep watching. So the specifics of how path compression works can be found in page 156 in the textbook. But I'm just going to show you how like visually what's going on during path compression. So the idea of path compression can be thought of as a form of caching. Basically, when I call find once, I already know a lot about the item. So say I want to know if 7 and 9 are connected. The way I do that is I call find on 7 and I call find on 9. So when I call find on 7, what's actually going on is I go to this item 7 at the array and I look at what value it's stored. And in this representation, 3 is stored there. So I go to 3 and I go to index 3, and at index 3, 1 is stored there, and I go to index 1, and index 1, 0 is stored there. And so in that process, I've iterated over 3 nodes. But the next time when I call find 7, I know, well, the value is not going to change, right? Because once something is added to the set, we no longer can like remove it from the set, right? So I can basically kind of make subsequent calls to find 7 a lot faster by moving the node from down here all the way up directly connecting it to the grandparent node. And in terms of what this actually does to the array is that at index 7, I change it to 0, right? Because I know that its kind of grandparent, or the set it belongs to, is always going to be 0. And so same thing for 9. I call find on 9, I move it up. And next time when I call find on 7, so say for example, I'm trying to answer the question if 2 and 7 are connected, I call find on 2, and that's fine because it's already directly connected to 0, so nothing changes there. But now when I call find 7, it only takes me 1 step. And so, let's go back. So now this is how kind of path compression works. And you can have it be a little more extreme, right? Because in this example here, when I called find 7, I only moved 7 up, but I could also have moved 3 and 1 up, right? So there are different ways of implementing them. But the idea is that in terms of asymptotic time complexity, right? It doesn't really change anything because, at the end of the day, in the worst case scenario, you still have to traverse the entire tree on your first call. But where this path compression really shines is that subsequent calls to find would be much faster, right? And this, if you were to think of actual behavior or how somebody would actually use this, say that a member is really popular and is constantly being called, then doing path compression will significantly improve your runtime in a more kind of practical analysis. Okay, so that's the end of the video. Hopefully you found it helpful and hopefully you learned something new from the video. Now we're going to hopefully have this ed post for this video, and you can feel free to let us know any comments or any suggestions for this new format. Thank you.